I want to multiply, I'm going to drop the x's just so that the thing looks less complicated. So what I want to do is multiply this equation through by u of x. That's why it's called a factor, because you're going to multiply everything through by it. So it's going to look like uy prime plus p u y equals qu. And now this thing is, so far it's just a factor. What makes it an integrating factor is that this, after I do that, I want this to turn out to be the derivative of something with respect to x. You see the motivation for that? If this turns out to be the derivative of something because I've chosen u so cleverly, then I'll be able to solve the equation immediately just by integrating this with respect to x and integrating that with respect to x. You just then integrate both sides with respect to x, and the equation is solved. Now, the only question is, what should I choose for u? Well, if you think of the product formula, there might be many things to try here, but there's only one reasonable thing to try. Try to pick u so that it's the derivative of u times y. See how reasonable that is. If I use the product rule on this, the first term is u times y prime. The second term would be u prime times y. Well, I've got the y there, so this will works if what? If, what's the condition that u must satisfy in order for that to be true? Well, it must be that after I do the differentiation, u prime turns out to be p times u. So is it clear? This is something we want to be equal to, and the thing I'll try to do it is by choosing u in such a way that this equality will take place, and then I'll be able to solve the equation. And now, so here's what my u prime must satisfy. Hey, we can solve that, but please don't forget that p is p of x. It's a function of x. So if you separate variables, I'm going to do this. So what is it? du over u equals p of x times dx. If I integrate that, so separate variables, integrate, and you're going to get du over u integrates to be the log of u, and the other side integrates to be the integral of p of x dx. And you can put an arbitrary constant there, or you can think of it as already implied by the indefinite integral. Well, that doesn't tell us yet what u is. What should u be? Notice I don't have to find every possible u which works. All I'm looking for is one. All I want is a single u which satisfies that equation. Well, u equals the integral e to the integral of p dx. That's not too beautiful looking, but by differential equations, things can get so complicated that by the, in a week or two, you will think of this as an extremely simple formula. So there's the formula for our integrating factor. We found it. We'll always be able to write an integrating factor. Don't worry about the arbitrary constant because you only need one such u. So no arbitrary constant since only one u needed. And that's the solution, the way we solve the linear equation. Okay, let's take over and actually do it. I think it would be better to summarize it as a clear-cut method. So let's do that. So what's our method? It's the method for solving y prime plus py equals q. Well, the first place, make sure it's in standard linear form. If it isn't, you must put it in that form. Notice the formula for the integrating factor. The formula for the integrating factor involves p. the integral of p dx, so you better get the right p. Otherwise, you're sunk. Okay, so put it in standard linear form. That way you'll have the right p. Notice that if you wrote it in that form, and all you remembered was integral e to the integral p dx, the p would have the wrong sign. That, if you're going to write that p, should have a negative sign there. So do it this way and no other way. Otherwise you'll get confused and get wrong signs, and as I say, that will produce wrong answers, and not just slightly wrong answers, but disastrously wrong answers from the point of view of the modeling, if you really want answers to physical problems. So here's a standard linear. Then find the integrating factor. So calculate e to the integral p dx, the integrating factor. And then multiply both. I'm putting this as both. Underline that as many times as you have room in your notes. Multiply both sides by this integrating factor by e to the integral p dx. And then integrate. Okay, let's take a simple example. Suppose we started with the equation xy prime minus y equals, I had a x squared, x cubed, something like that. X cubed, I think. Yeah, x cubed. Okay. What's the first thing to do? Put it in standard form. So step 0 will be to write it as y prime minus 1 over x times y equals x squared. There are two standard errors. Let's do the work first, and then I'll talk about mistakes. And now what? Well, we now calculate the integrating factor. So that's, I do it in steps. You can integrate negative 1 over x, right? That integrates to minus log x. So the integrating factor is e to the integral of this dx, so it's e to the negative log x. Now in real life, that's not the way to leave that. What is e to the negative log x? Well, think of it as e to the log x to the minus 1. Or in other words, it is e to the log x is x, so it's x to the minus, so it's 1 over x. So the integrating factor is 1 over x. Okay? Multiply both sides by the integrating factor. Both sides of what? Both sides of this, the equation written in standard form, and both sides. So it's going to be 1 over x y prime minus 1 over x squared y is equal to x squared times 1 over x, which is simply x. Now, if you have done the work correctly, you should be able now to integrate the left-hand side directly. So I'm going to write it this way. I always recommend that you put in as an extra step, well, I won't. Put in as an extra step the reason for using that integrating factor. In other words, that the left-hand side is supposed to be now 1 over x times y prime. I always put in that because there's always a chance you made a mistake or forgot something. Look at it, mentally differentiate it using the product rule just to check that in fact it turns out to be the same as the left-hand side. So what do we get? 1 over x times y prime plus y times the derivative of 1 over x, which indeed is negative 1 over x squared. And now finally, that's 3a. Continue, do the integration. So you're going to get, let's see if we can do it all on one board. 1 over x times y is equal to x plus a constant, x squared over 2 plus a constant. And the final step will be, therefore, I now want to isolate y by itself. So y will be equal to, multiply through by x cubed over 2 plus c times x. And that's the solution. Okay, let's do one a little slightly more complicated. Let's try this one. Now my equation is going to be 1. I'll still keep 2, y and x as the variables. I'll use t in a minute or two. 1 plus cosine x. So I'm not going to give you this one in standard form either. Trick question. Y prime minus sine x times y is equal to anything reasonable, I guess. I think what x 2x. Make it more exciting. Okay. Now, I think I should warn you where the mistakes are, just so that you can make all of them. So this is mistake number 1. You don't put it in standard form. Mistake number 2, generally people can do step 1 fine. Mistake number 2 is you don't. This is my most common mistake, so I'm very sensitive to it. But that doesn't mean if you make it, you'll get any sympathy from me. I don't give sympathy to myself. You're so intent on, so happy at having found the integrating factor, you forget to multiply q by the integrating factor also. You just handle the left-hand side of the equation, and you forget about the right-hand side. So the emphasis on the both here is the right hand, please include the q. Please include the right-hand side. Any other mistakes? Well, nothing that I can think of. Well, maybe only. Anyway, we're not going to make any mistakes for the rest of this lecture. So what do? We write this in standard form. So it's going to look like y prime minus sine x divided by 1 plus cosine x times y equals, my heart sinks because I know I'm supposed to integrate something like this, and boy, that's going to give me problems. Okay, well, not yet. What's the integrating factor? The integrating factor is, well, we want to calculate the integral of negative sine x over 1 plus cosine. That's the integral of p dx. And after that, we have to exponentiate it. Well, can you do this? Yeah, but if you stare out a little while, you can see that the top is the derivative of the bottom. That is great. That means it integrates to be the log of 1 plus cosine x. Is that right? 1 over 1 plus cosine x times the derivative of this, which is negative cosine x. Therefore, the integrating factor is e to that. In other words, it is 1 plus cosine x. Therefore, so this was step 0. Step 1, we found the integrating factor. And now step 2, we multiply through by the integrating factor. And what do we get? We multiply through the standard form equation by the integrating factor. And if you do that, what you get is, well, y prime gets the coefficient 1 plus cosine x. Y prime minus sine x equals 2x. Oh dear. Well, I hoped somebody would giggle at this point. What's giggleable about it? Well, that all this was totally wasted work. That's called spinning your wheels. No, it's not spinning your wheels. It's doing what you're supposed to do and finding out that you wasted the entire time doing what you were supposed to do. Well, we get, in other words, the net effect of this is to end up with the same equation we started with. But what is the point? The point is of having done all this was because now the left-hand side is exactly the derivative of something, and the left-hand side should be the derivative of what? Well, it should be the derivative of 1 plus cosine x times y, all prime. Now, you can check that that's in fact the case. It's 1 plus cosine x, y prime, plus minus sine x, the derivative of this side, times y. So, if you had thought, in looking at the equation, to say to yourself, this is the derivative of that, maybe I'll just check right away to see if it's the derivative of 1 plus cosine x sine y, you would have saved that work. Well, you don't have to be brilliant or clever or anything like that. You do it, you can follow your nose, and it's just, I want to give you a positive experience in solving linear equations, not too negative. Anyway, so we got to this point. So this is 2x, and now we're ready to solve the equation, which is, the solution now will be 1 plus cosine x times y is equal to x squared plus a constant, and so y is equal to x squared divided by x squared plus a constant divided by 1 plus cosine x. Suppose I had given you an initial condition, which I didn't, but suppose the initial condition said that y of 0 were 1, for instance. Then the solution would be, so this is an if, I'm throwing in at the end just to make it a little bit more of a problem. How would I then I could evaluate the constant by using the initial condition. What would it be? This would be, on the left-hand side, 1. On the right-hand side would be c over 2. So I would get 1 equals c over 2. Is that correct? Cosine of 0 is 1, so that's 2 down below. Therefore, c is equal to 2, and that would then complete the solution. It would be x squared plus 2 over 1 plus cosine x. Now, let's, you can do this in general, of course, and get a general formula, and we'll have occasion to use that next week. But for now, why don't we concentrate on the most interesting case, namely that of the linear equation with constant coefficient. That is, so let's look at the linear equation with constant coefficient, because that's the one that most closely models the conduction and diffusion equations. So what I'm interested in is, since this is of them all, probably the most important case is the one where p is a constant, because of its application to that, and many of the other, the bank account, for example, all of those would use a constant coefficient. So how is the thing going to look? Well, I'll use the cooling. Let's use the temperature model, for example. The temperature model, the equation will be dt dt plus kt is equal to, now notice on the right hand side, this is a common error, you don't put TE, you have to put KTE, because that's what the equation says. If you think units, you won't have any trouble. Units have to be compatible on both sides of a differential equation, and therefore whatever the units were for capital KT, I'd have to have the same units on the right hand side, which indicates I cannot have KT on the left of the differential equation and just T on the right and expect the units to be compatible. That's not possible. So that's a good way of remembering that if you're modeling temperature or concentration, you have to have the K on both sides. Okay, let's do, now a lot of this we're going to do in our head now, because this is really too easy. What's the integrating factor? Well, the integrating factor is going to be the integral of k, the coefficient now is just k, p is a constant k, And if I integrate k dt, I get kt. And I exponentiate that, so the integrating factor is e to the kt. I multiply through both sides, multiply by e to the kt, and what's the resulting equation? Well, it's going to be, I'll write it in the compact form, it's going to be e to the kt times t, all prime. The differentiation now, of course, is with respect to the time, and that's equal to k t e, whatever that is, times e to the kt. This is a function of t, of course, the function of little time. Sorry, little t time. Okay, and now finally we're going to integrate. What's the answer? Well, it is e to the, so we're going to get e to the kt times t is, sorry, k little t, k times time times the temperature is equal to the integral of k te, I'll put the fact that it's a function of t inside just to remind you, e to the kt, and now I'll put the arbitrary constant. Let's put in the arbitrary constant explicitly. So what will t be? Okay, t will look like this finally. It will be e to the negative kt, that's on the outside. Then you will integrate. Of course, the difficulty of doing this integral depends entirely upon how this external temperature varies. But anyway, it's going to be k times that function which I haven't specified, e to the kt, plus c times e to the negative kt. Now, some people, many in fact, and almost always in the engineering literature, almost never write indefinite integrals, because an indefinite integral is indefinite. In other words, this covers not just one function, but a whole multitude of functions which differ from each other by an arbitrary constant. So in a formula like this, there's a certain vagueness, and it's further compounded by the fact, I don't know whether to put whether the arbitrary constant is here. I seem to have put it explicitly on the outside the way you're used to doing from calculus. Many people therefore prefer, and I think you should learn this, to do what is done in the very first section of the notes called definite integral solutions. They like, if there's an initial condition saying that the internal temperature at time 0 is some given value, what they like to do is make this thing definite by integrating here from 0 to t and making this a dummy variable. You see what that does is it gives you a particular function, whereas it was a, I'm sorry I didn't put in the dt one, woo, minus 2. What it does is that when time is 0, all this automatically disappears, and the arbitrary constant will then be, well, it's t, so in other words, c times this, which is 1, is then equal to t. In other words, if I make this 0, then I can write c as equal to this arbitrary starting value. Now, when you do this, the essential thing, and we're going to come back to this next week, but right away, that because k is positive, I wanted, since I emphasized that so much at the beginning of the period, I want to conclude by showing you what its significance is. This part disappears because k is positive, the conductivity is positive, this part disappears as t goes to 0. This goes to 0 as t goes to infinity. So this is the solution that remains. This, therefore, is called the steady state solution, the thing which the temperature behaves like as t goes to infinity. This is called the transient because it disappears as t goes to infinity. It depends on the initial condition, but it disappears, which shows you that in the long run, for this type of problem, the initial condition makes no difference. The function behaves always the same way as t goes to infinity.